ሰላም እንደገና ይሄ ሁለተኛው ፓርታችን ነው። በአድቫንስድ ኤሮስፔስ ኢንጂነሪንግ ሴክሽን የምናየው አስትሮናውቲክስ ነው። ሪካፕ ለማድረግ ኤሮስፔስ ኢንጂነሪንግ ለሁለት ይከፈላል ብለናል። ኤሮናውቲክስ እና አስትሮናውቲክስ። አሁን ዲል የምናደርገው በአስትሮናውቲክስ ነው። አስትሮናውቲክስ እንግዲህ እንደተነጋገርነው it deals with anything that is applicable in space, which includes rockets, satellites, different things, including missiles. Anything is related to astronautical engineering. So, a space propulsion application, which is the propulsion. It's the way of generating thrust to move a spacecraft or an airplane into the air or into space. So, launch vehicle launch rocket with ground up to an ascent flight into space launch use propulsion space propulsion application. Another is ballistic missiles. Ballistic missiles are similar. They're just having the same mechanisms of rockets. Ballistics, they carry a different payload. Ballistic missiles, it's a bomb. It's an explosive bomb. So we call them missiles, right? So when it comes to rockets, the payload is different. You can send a satellite, you can send a human as a payload on board that missile. As orbiting satellites, they're part of space propulsion application. Your upper stages, which means propelling a capsule with the more satellite and the space light. Propel ለማድረግ you use an upper stage. ሌላኛው interplanetary spacecraft ነው, which is basically the Apollo spacecraft which sent humans to the moon. It uses a space propulsion system. ይሄ ነው። ሌላኛው ደግሞ manned space flight ነው, which is basically going to the moon or going to the International Space Station, requires space propulsion. So it's one of the space propulsion application. So space propulsion function, we classified it into two. Launch and descent. Launch and descent is launching a rocket into space that requires a huge amount of power, which could be the primary propulsion. So maneuvering. Maneuvering means to transfer from one orbit to the other, or it could be keeping your altitude in space, and also you can correct your trajectory. So we don't we don't just go straight to the moon, not burning our fuel. And this way, that's the inefficient way of going to space. So we would be missing the moon. So assume that we have a trajectory. Trajectory gravity we have orbits. So an orbit when we reach our maximum point of our orbit, or when we reach at some point in our orbit, we may meet the planet. So that way we can move into space. And space travel. Now maneuver in space, we use propulsion systems. So one of these space propulsion application is maneuvering. So auxiliary propulsion system, which means a secondary propulsion function, meaning attitude control. Attitude and altitude are very different things. So when you say altitude, you're measuring the distance. For example, altitude of a satellite a kilometer. For example, if Aerospace one has an altitude of, let's say, 700 or 600 kilometers, but then that we're mentioning or referring to the altitude of the spacecraft. When we say altitude, it's basically meaning that the orientation of your spacecraft, which means your orientation in some angle, in some reference frame, spacecraft orientation, we call that altitude. Reaction control double. There's always different forces in space. Even though it's a vacuum, you got solar forces like photons hitting your spacecraft. ስለዚህ እነሱ across time accumulate ያደርጉና trajectoryያችሁ ላይ የሆነ small change ያመጣሉ. That small change could be disastrous. You may miss your final destination. ስለዚህ እሱን remove ለማድረግ they are reaction controlling small mechanisms or propulsion systems to help you keep up with your trajectory. Momentum management, for example, if you want to dock to the International Space Station, so you fire up your engines. So you have to slow down whenever you want to slow down, you have to fire up in the reverse direction. So with the reverse direction fire up ለማድረግ you need to manage your momentum. So we call that auxiliary propulsion systems. It's part of the auxiliary propulsion system. ይሄ ምን ማለት ነው? For example, ለምሳሌ ስፔስ ክራፍታችሁን 90 ዲግሪ ሮቴት ማድረግ ካለባችሁ 90 ዲግሪ ሮቴት ለማድረግ በሆነ ዲስታንስ from the center of mass የሆነ ኢንጂን አስቀምጣችሁ ያ ኢንጂን ፋየር አፕ ሲያደርግ ሮቴት ያደርጋል። ግን ኢንጂኑ ከቆመ በኋላ as you know ስፔስ እንደ ቫኪዩም በመሆኑ ምክንያት ሮቴሽኑ አይቆምም፣ ሮቴሽኑ ይቀጥላል። ያንን ሮቴሽን ማቆም አለባችሁ። So you have to manage your momentum. Your change in momentum needs to be zero if you want to keep your spacecraft in that specific orientation. Now in the reverse direction 90 degree for a certain period of time ሌላኛውን ኢንጂናችሁን ፋየር አፕ ማድረግ አለባችሁ። So this is an example of the space shuttle እንዴት attitude control እንዴት እንደምንጠቀም ነው። ከኋላ ደግሞ የምታያቸው maneuver ለማድረግ የምትጠቀሙባቸው ኢንጂኖች ናቸው። So a brief history of Rocketry. Rocketry was recorded in China 300 BC. Mostly they use it for war, and also they used it for fireworks. ስለዚህ black powder ነው የመጀመሪያው mostly earlier known የሆነው propellant black powder ነው። black powder ተቀጣጣይ የሆነ mixture. So you can use black powder. I think it's a combination of sulfur and then a sulfur combination with potassium nitrate gives you that kind of black powder. I think there's a sulfur and then potassium nitrate that gives you black powder. Yeah. So and an interesting fact, Wanhu was he was one of the person who tried to launch himself into space with 14 black powder rocketoችን አንድ ወንበር ላይ አታች አደረገ። ከዛ በኋላ ከለኮሰ በኋላ ግን it's like a myth እና he just disappeared out of nowhere. He just disappeared and nothing was there. And now this was one of the earliest trial of space exploration, I guess. So Russia in the early 90s, Konstantin Tsiolkovsky, who is considered as the father of rocketry, orbital mechanics ላይ የምታገኛቸውን ኢኩዌሽኖች ሮኬት ኢኩዌሽኖችን ድራይቭ ያደረገው እሱ ነው ማለት ነው። When it comes to the United States in the 1926, I guess Dr. Robert Goddard was the first person to ever design and build a liquid fueled rocket engine. Liquid fueled rocket engine እንግዲህ it's the basis አሁን ያለንበትን ደረጃ ያገኘነው በሊኩዊድ fueled rocket engine. Without him we won't be able to go to the moon, we won't be able to launch our satellites only with a solid rocket powered engine. ምክንያቱም solid rocket powered engine, for example black powder ስትጠቀሙት solid powered rocket engine ምክንያቱም you're using your atmosphere's oxygen to oxidize your fuel. ነገር ግን liquid rocket engine it carries its own liquid oxidizer, or it could be a gas oxidizer or oxygen, and then you use your onboard oxidizer with your onboard fuel to generate combustion. ይሄ ነው የሚሆነው ማለት ነው። ሌላኛው Germany in 1940s, Dr. von Braun, most of you know it. He's the inventor of the V2 rocket, and then when von Braun was also part of NASA's program, he was the mastermind behind the Saturn V rocket, which sent humans to the moon. And as you know, Hermann Obertsum, he's a German scientist. እሱ ደግሞ የተለያዩ orbital transfer ሜቶዶችን ክሬት አድርጓል። በኋላ የምናየው ነገር ይሆናል። Space propulsion system, it's divided into basically into four. The first one is stored gas. Chemical is divided into solid, liquid, hybrid, and liquid is categorized into four different categories based on the pressure system and how it uses to generate thrust. እና ፓምፕ ነው የሚጠቀመው፣ ፕሬሸር ነው የሚጠቀመው፣ እንዴት ነው ውስጥ ያሉት ሊኩዊዶች ፍሎ ለማድረግ የሚጠቀምበት ሜካኒዝምን በሱ ኬሚካል ፕሮፖልሽን ሲስተም ለሊኩዊድ ኬሚካል ፕሮፖልሽን ሲስተምን ለአራት ይከፍላል። ሃይብሪድ ደግሞ የሶሊድ እና የሊኩዊድ ቅልቅል ነው። ኤሌክትሪክ ፕሮፖልሽን ሲስተም ራሱን የቻለ ፕሮፖልሽን ሲስተም ነው። ኤሌክትሮስታቲክ፣ ኤሌክትሮዳይናሚክ and then more advanced ደግሞ ስናደርገው nuclear, solar, laser and then antimatter propulsion system. So these are classified based on the energy that they use. Is it a chemical energy? Is it a electrical energy? Is it a more advanced type of energy like nuclear, solar, or laser, or is it just a gas? So this classification is used to classify space propulsion systems. So የመጀመሪያው stored gas propulsion system ነው. You have a stored gas, it's pressurized, so you control the pressure with a pressure gauge, and then high pressure gas በሚወጣበት ጊዜ you gain thrust ማለት ነው. Thrustን እንደዚህ ዴቨሎፕ ማድረግ ትችላላችሁ ማለት ነው. Thrusteሮቹ is just a nozzle pressure difference ይፈጥራል. ያ pressure difference additional thrusትን generate ማድረግ ይችላል. Propellant include example nitrogen, helium, nitric oxide, and butane are part of a propellant used for stored gas propulsion system. An example I would say would be the International Space Station. It uses a stored gas propulsion systems, mostly እነዚህ በጣም ይጠቅማሉ ለaltitude controlling system, because you don't want to burn a fuel and an oxidizer at the same time just to rotate your spacecraft. And now stored gas propulsion system, ለምሳሌ air could be used as a stored gas propulsion system, but mostly nitrogen, helium, and nitric oxide and butane are used as a propellant for a stored gas propulsion system. Example is that as a real life example, ለምሳሌ ፊኛ ሞልታችሁ ፊኛውን አየር ነፍታችሁበት ብትለቁት ምንድነው የሚሆነው? ውስጡ ያለው highly pressurized የሆነ አየር ፊኛውን እየገፋ it wins in a chaotic movement, right? So that is a stored gas propulsion system. So we have a chemical propulsion system. So how do we classify chemical propulsion system? We have a liquid propellant. So liquid propellant is classified as pump-fed, pressure-fed, monopropellant, and bipropellant. So monopropellant in general, monopropellant is just you just only have a fuel. So you only have a fuel. You don't have an oxidizer. Just the fuel is liquid. Bipropellant, you're going to have a fuel and also at the same time another tanker for an oxidizer ማለት ነው. ፓምፕ ፌድ ደግሞ ማለት እነዚህ ኦክሲዳይዘር እና ፊውሉን ለማንቀሳቀስ you use a pump. So the pump ያደርጋል ፊውሉንም ኦክሲዳይዘሩንም just in a different cycle በኋላ እናያለን. ፕሬሸር ፌድ ደግሞ the ኦክሲዳይዘሩ እና ሊኩዊዱ በሳይክል ውስጥ ሙቭ የሚያደርጉት using the pressure. There is a highly pressurized liquid that forces the oxidizer and the liquid to move in any cycle. Hybrid ደግሞ solid እና liquid አንድ ላይ በማቀላቀል የሚሰራ propulsion system ነው. Sounding rocket expires እንደምታዩት እዚህ ጋር hybrid rocket engine for space flight. Spaceship One, I mean the Virgin Galactic Spaceship One uses this type of propulsion system. Solid propellant ደግሞ you don't have a you don't have a liquid propellant, and also you don't have an oxidizer tank to provide oxidation of your fuel. Instead, you're going to use your atmosphere's oxygen to burn your fuel. ሌላኛው monopropellant system ነው. So monopropellant system በምናይበት ጊዜ there's only a single fuel. ቀደም እንዳልኩት hydrazine, for example, is the most common monopropellant system. So hydrazine monopropellant system ነው እና ያንን fuel you're going to catalyze it. You're going to catalyze it. So catalyze በምታደርጉበት ጊዜ ከላይ እንደምታዩት nitrogen or helium አለ. Nitrogen or helium ከhydrazine ጋር በሚገናኙበት ጊዜ hot gas ይፈጥራሉ. It's not combustion. It's a different process because catalyst በሚጨምሩበት ጊዜ you get a different thing other than combustion. ያ process ደግሞ high pressure hot gas produce ያደርጋል. ያ hot gas ደግሞ በትረስተሮች ላይ distribute ያደርግና you produce thrust ማለት ነው. So they additionally bipropellant system አለ. Bipropellant system it uses a fuel and an oxidizer. So the fuel and the oxidizer are fed into the combustion chamber with some kind of system. So bipropellant systems use both fuel and oxidizer tanker አላቸው ማለት ነው. So there are two types of ignitions. ወይም ደግሞ bipropellant systems are. የመጀመሪያው hypergolic bipropellant system, which means you don't need igniters. When you make the fuel and the oxidizer in contact, ራሳቸው combustion ይፈጥራሉ ካለምንም ignition ማለት ነው ወይም ደግሞ ካለምንም igniter ignition መፍጠር ይቻላል። cryogenic propellant ደግሞ ምንድነው ግዴታ ሁለቱ in contact ቢሆኑ oxidizer እና fuel you need some kind of ignition or igniter is required to produce combustion. Let's say liquid oxygen and liquid hydrogen, these are cryogenic propellant. They are mostly used in many of the engines currently available today. So liquid propellant, we have pump-fed systems. Pump-fed system, there is a big pump. That pump, it's a gas turbine pump. Yeah, pump is going to use some kind of fluid, and then that fluid is going to push the fuel and also the oxidizer to the combustion chamber. Because when you think of it, let's say that you are on Earth, and now fuel tank ወይም oxidizer tank ወደ combustion chamber, gravity could do the job of feeding those liquids into the combustion chamber. But when you go to space, you don't have gravity to pull your fuel and oxidizer to the combustion chamber. So what you need is you need some kind of pushing system. That pushing system could be a pump. So the pump could push your fluids into the combustion chamber. For example, F1 engine, የራሱ የሆነ turbo pump አለው እና it has 55,000 horsepower, and then it uses for example ብሰጣችሁ የሆነ pool ቢኖራችሁ how efficient is it ይሄንን describe ለማድረግ if you have a pool in your backyard እና እሱ ውስጥ ያለው ውሃ 18,000 gallons of ውሃ ቢሆን ያንን gallons of ውሃ በዚህ horsepower የአንድ F1 engine turbo pump it's going to pump it within 27 seconds. So ማየት የምትችሉት these pumps deal with a larger volume of fuel and also oxidizer. So የመጀመሪያው power cycle, it's a gas generator cycle. It's the simplest. It's one of the most common that you can find with engines. So ምንድነው generalize ለማድረግ ምንድነው this power cycle ምንድነው መጀመሪያ fuel ይገባል የገባው fuel it's going to get into a gas generator. So gas generator ደግሞ oxidizer-ን እና fuel-ን ተጠቅሞ ትንሽዬ combustion ይፈጥራል። ከዛ combustion የሚገኝ energy ተርባይኑን rotate ያደርጋል። ያ ተርባይኑ መልሶ it's connected with the shaft, with the fuel pump, and also with the oxidizer. So continuously oxidizer እና ፓምፑን ከfuel tank እና oxidizer ታንኩ draw ያደርጉ ወደ combustion chamber ያስገባል ማለት ነው። This is just a continuous process of going over and over and over again. So pampu, it's powered by a gas generator. For example, F1 engine uses a gas generator cycle just to use a turbine. The turbine is just like a turbo pump engine. And then you have another power cycle, which is the expander cycle. The expander cycle, you don't have a gas generator. The gas generator is missing from this diagram because fuel ይገባል fuel ከገባ በኋላ ቀስ ብሎ በሞቀው የኖዝል ሳይድ በሚሄድበት ጊዜ ኤነርጂ ይጨምራል and then ኤነርጂ የጨመረው fuel ተርባይኑን ያንቀሳቅሳል ተርባይኑ ደግሞ it's connected with the fuel pump and also it's connected with the oxidizer pump. So በሻፍት ኮኔክትድ የሆኑት እነዚህ ሁለት ነገሮችን በሚያንቀሳቅስበት ጊዜ continuously oxidizer fuel continuously ወደ combustion chamber drive ያደርጋል ማለት ነው። ከዚህ ውስጥ ኤግዛምፕል የምናይበት Pratt & Whitney RL10 engine ነው the picture ላይ እንደምታዩት it produces sufficient energy to drive the turbine and also it is high performance than the gas generator cycle. ሶስተኛው stage combustion ነው stage combustion it uses በጣም complicated እና sophisticated የሆኑ turbo machinery ነው የሚጠቀመው turbo machinery means the gears, the turbine, but they're complicated in their orientation and how they're used to help the fuel pump and then the oxidizer pump. ስለዚህ እንዴት ነው የሚሰራው? There is a preburner. It's basically similar with the gas generator cycle. So fuel ይገባል, and then the preburner oxidizer እና fuel ያቀጣጥላል, and then the turbine turbine ያንቀሳቅሳል. So turbine ያንቀሳቅሳል, it has to get back to the combustion chamber. So ወደ combustion turbine አንቀሳቅሶ ከፕሪበርነሩ የተገኘው ያ ኤነርጂ turbine አንቀሳቅሶ the leftover needs to get back to the combustion chamber. This is the basic difference between the stage combustion and the gas generator cycle. Now it's not very common. Example is the SSME 2700 PISA engine. It's an example of this cycle. So big engine. So how large is an engine? So an F1 Saturn V5 engine, which sent humans to the moon. This engine, 5 of these engines were used in the first stage of the Saturn V engine, of the Saturn V rocket. Sorry. Now, size of how large it is, how the nozzle is very huge, how the turbo machineries are illustrated in the picture. Main engine, the space shuttle main engine, it's not that much bigger. It's not like the F1 engine, but it's kind of smaller. And the main engine of the space shuttle, there are I think 3 main engines for the space shuttles. So this is another engine, RD-170, and you can see the thrusts. One of the biggest thrust provider from these 3 engines is the Saturn V F1 engine with 1.5 pounds of thrust force, and then you can see and then you have the F1 engine with Saturn V. You have 1.5 millions of pounds thrust, and then you have the RD-70, because the RD-70 has 4 different engines. You can see that it's the largest thrust provider in this scenario, I guess. So solid propellant motors. Solid propellant motors, as I have said, that they are in a solid binder. So your oxidizer and then your fuel are just in a binder. So solid propellant እንደዚህ ነው የሚሰራው ማለት ነው። Single use, you're not going to start it again. When you fire up a solid propellant rocket engine, there is no turning it off. ለምሳሌ solid liquid engine ቢሆን ኖሮ በፈለጋችሁበት ሰዓት ኮምበስሽን ተቆጣጥራችሁ ልታበሩ ትችላላችሁ። ግን በsolid propellant ጊዜ ግን there is no turning it off. Once you fire up your rockets, that was it. በቃ ባንዴ ኮምበስት አድርገው ነው የሚያልቀው ማለት ነው። They are low performance, and then they don't have this, the gas generator cycle, any cycle to push the fuel and the oxidizer into the combustion chamber. Just the oxidizer and fuel, they are just in a metal binder. And launch vehicles upper stage, basically helper boosters. So ለምሳሌ solid booster SRBs are solid rocket boosters, which uses solid propulsion. So rocket performance. How do we calculate rocket performance? So የመጀመሪያው is thrust. So thrust is the amount of force generated by a rocket engine, and then you have specific impulse. So specific impulse ምንድነው? It's the measurement of የአንድ engine performance measurement ያደረገበት መንገድ ነው። So we have specific impulse. Specific impulse ምንድነው? The force divided by the weight flow rate of the propeller. Generate የተደረገው force to the ratio of ምን ያህል ነው propellant በምን ያህል rate ነው propellant lose እያደረግን ያለው, which means it's like mass of the propellant per second, right? So if you have a higher specific impulse, let's say you have a very high specific impulse, which means the force divided by the weight flow rate of the propellant means the weight divided by the second. So the specific impulse is it's given by second mass. So the specific impulse, its units are seconds, because when you divide the force by weight per second, you're left with second. ምክንያቱም የፎርስ እና የዌት እንደምታውቁት their units are newtons. ስለዚህ when you have force, you have the thrust force divided by the propellant rate. So if you have a very small propellant rate, but at the same time you're producing a very high amount of thrust force, then you have a very high specific impulse, which means በጣም efficient የሆነ engine አላችሁ ማለት ነው. So the rocket equation is change in delta, which is the change in velocity, g, the gravity times the specific impulse, and lan as a function of the initial mass divided by the final mass. So this is the delta, change in delta v metagonist. So the propellant mass is given by the initial mass times 1 minus the exponential function with e raised to minus change in v over g times the specific impulse. So this formula is derived from the rocket equation. rocket equation derived. So delta v mission requirement which is now. So the ከመሬት ተነስታችሁ ወደ lower orbit ለመሄድ you need 7.6 kilometer per second delta v. እዚህ ፎርሙላ ላይ የምታዩትን delta v ማለት ነው. You need 7.6 kilometer per second delta v from lower orbit. ከlower orbit ወደ earth escape, which means ከመሬት gravitational pull መውጣት ከፈለጋችሁ you need to have a change in velocity of 3.2 kilometer per second. And ከlower orbit ወደ Mars ደግሞ መሄድ ከፈለጋችሁ it requires 0.7 years, around 6 to 7 months. So that would require you a 5.7 kilometer per second change in your velocity. Lower orbit with a Neptune, it will require 29.9 years, and that will require you 13.4 kilometer per second. So we have different scenarios. For example, if you want to go from lower orbit to the Alpha Centauri, which is the nearest star, it will require you 50 years, but then the delta v will be much higher, 30,000 kilometers per second. This is an insane speed when you think of it, because the technology that we have in changing delta v produce matter, it's literally one of the hurdles of in aerospace engineering. Propellant calculation exercise. So for example, we want to go from lower orbit to Mars. So it requires 0.7 years. And now it's a thing, spacecraft mass. We are required many half propellant ነው የሚያስፈልገው. ምን ያህል propellant በርን ብናደርግ ነው ከሎወር ኦርቢት ወደ ማርስ መሄድ የምንችለው? So we use the rocket equation. ቅድም ያየነውን rocket equation ነው የምናየው ማለት ነው. Yeah, this one. So rocket equation እንጠቀማለን. engine v, you have this, and then you have the mass propellant. ከዚህ ፎርሙላ ድራይቭ የተደረገው ነው. ስለዚህ ይሄን ፎርሙላ ተጠቅማችሁ you can get the amount of propellant mass required. So using the equation, we have 2,117 kilograms, and this is the mass of the propellant. So በምታዩበት ጊዜ your spacecraft, the whole package is 2,500 kilogram. The whole package, including the fuel and then including your propellant. So ከዚህ ማየት መረዳት የምንችለው መላክ የምትችሉት payload, it's only 383 kilograms is left. So that is the only mass that is left that you can send into space. That's why space travel is expensive, because most of your mass in meso propellant and propellant is really expensive. And how can we improve this? So this is a question that we have to achieve in efficient engineering in the aerospace sector. So thermodynamic rocket እንዴት ነው የሚሰራው? So F equals to m dot VE plus this is the PE means the exit pressure minus the A, you got the ambient pressure, and then times the area of the exit. So this gives you the thrust force of the rocket engine. So for an ideal expansion, which means you literally not going to have a change in pressure before the ambient and then in the exit. So for ideal expansion, you're going to have your thrust force equals to m dot times the exit velocity. M dot is the mass flow rate of your fuel and your oxidizer. So nozzle expansion might እንችላለን when you have a matched pressure, which means your thrust equation which is going to be F equals to m dot times VE, which VE is the exit velocity. So slightly expand በምታደርጉበት ጊዜ ምንድነው nozzle it's doing its job because you have the exit pressure is greater than the ambient pressure. So when you minus that and then multiply it with the area of the exit nozzle, you can get a higher thrust than a matched pressure. ሌላኛው ደግሞ slightly overexpanded ነው. Slightly overexpanded በሚሆንበት ጊዜ the nozzle is doing against your engine because you're going to this is going to decrease the thrust already produced with the exit velocity. ሌላኛው ደግሞ separated flow ነው, which means the ambient pressure is very high, so you're having a lower thrust compared to the other expansion methods. So conic nozzle አለ, ideal nozzle አለ, bell nozzle አለ. So these are different types of nozzle orientations. These will alter your amount of thrust produced. So electric propulsion, it could be thermal, electrostatic, and then electromagnetic. These are the types of electric propulsion systems. Electric propulsion systems, their specific impulse በምትበት ጊዜ specific impulseአቸው it could be very high. ነገር ግን the amount of thrust produce የሚያደርጉት ግን it is very slow. ስለዚህ ትረስቱ በጣም ትንሽ ስለሆነ specific impulse ትልቅ ቢሆንም efficient የሚሆኑት for a longer time ነው ማለት ነው። ለምሳሌ if you want to send a probe to Alpha Centauri, electric propulsion system ወይም ደግሞ nuclear propulsion system ተጠቅማችሁ you can send a probe to Alpha Centauri because even though produce የሚደረገው thrust በጣም ትንሽ ቢሆንም over time ግን accumulate እያደረገ accelerate ያደርጋል እንትናችሁ spacecraftአችሁ ማለት ነው። So ለምሳሌ Xenon ion engine is one of the example. It was designed and produced at the NASA's Jet Propulsion Laboratory, or known as JPL, and it's the first non-chemical propulsion system. Spacecraft primarily space propulsion system primary purpose propel matter. It could be used for maneuvering, and it's the first one used to propel a spacecraft and maneuver in space. So the last topic that we are going to see in the aerospace engineering advanced section is basics of orbital mechanics ወይም ደግሞ astrodynamics ይባላል። ለምሳሌ ይሄ ምንድነው የሚያጠናው? ለምሳሌ already satellite in space ካወጣችሁ በኋላ how does the satellite move in orbit? There is a science behind that. Or else ደግሞ how do we go to the moon? It's not like you in a spacecraft ውስጥ ገብታችሁ you want to ignite አድርጋችሁ just like the movies in the Star Wars engineering light up አድርጋችሁ you don't get to the moon or to Mars. That is the most inefficient way of going in space because space is very vast, but it's a larger distance, so you wouldn't be able to burn that much of fuel in that distance because you don't have the resources. So let's see orbital mechanics here. So what is orbital mechanics? Orbital mechanics or astrodynamics, it's an application of celestial mechanics. Celestial mechanics is a branch of physics which deals with the motion of planets, the sun, asteroids, different objects in space. So we are going to use this physics and then apply it to our man-made objects like satellites, like rockets, spacecraft. And not in principle ተጠቅመን ነው spacecrafቶች in space የሚያደርጉት ማለት ነው። So ከዚህ በተጨማሪ Newton's law of motion ወይም the laws of universal gravitation it's basically one of the most essential laws in orbital mechanics. So celestial mechanics and orbital mechanics ልዩነቱን በምናይበት ጊዜ ቅድም እንደነገርኳችሁ orbital mechanics it is the design of trajectories, maneuver ለማድረግ orbital plane changes, propulsive maneuvers. እነዚህም በአጠቃላይ it includes it's part of orbital mechanics. Celestial mechanics ደግሞ it's just the broad dynamics of any objects in space, and it includes astronomical bodies such as star systems, planet, moon, the comets. So ይሄ ነው በዋነኝነት and we also consider general relativity because it will help us to calculate orbits, and also it's very necessary to identify high gravity situations. So we'll be using this. So የመጀመሪያው idea in orbital mechanics is conic sections. So conic sections in the orbits are determined in different geometrical shapes. So the first one is a circle with eccentricity equals to 0, and then you have ellipse, which is between the eccentricity value of between 0 to 1, and then you got a parabola, which equals to 1, and then you got a hyperbola, which is eccentricity greater than 0. So ለምሳሌ parabolic flight ማየት የምንችለው ምንድነው? A plane could do a parabolic flight, and also a missile could do a parabolic flight, or a suborbital flight. Elliptical flight, elliptical orbit ደግሞ mostly our planet, the sun, also the moon and the satellites, they all use elliptical orbit. For a circle, I would say mostly satellites circle orbit ያላቸው satellites አሉ, and then hyperbola ደግሞ it's a flight path. Space flight path እንዴት ነው? ለምሳሌ ወደ ጨረቃ ብትሄዱ you're going to have at some point you're going to have a hyperbolic flight to reach the moon. So elliptical orbit geometry, just to recap on some of the basic stuff, you got R is your vector, your position vector, and then you got V is your velocity vector relative to the earth. So one in that essential ነገር ምንድነው orbital mechanics? Your reference frame is very essential. So V is a velocity vector, your relative velocity with respect to the earth, not with respect to any other reference frame. And then you got phi, you got your flight path angle, tangent line ወስዳችሁ ያላችሁ ይሄ tangential velocity የሚሰራው አንግል ነው. And then you got A, which is the semi major axis, and then that gives you 2 times that gives you the apogee, or the maximum distance from the object you're orbiting, and then you got B, the semi-minor axis, and then you got C, the distance between the center of your orbit to one of the foci. This is basically in geometry የምታገኛቸው property ነው, elliptical property ነው. So RA is the radius of apogee, and then RP is the radius of perigee. So radius of apogee means your distance from the earth, the maximum distance from the earth, and then radius of perigee is the minimum distance from the earth. So the picture depicted in the hono, you got the maximum distance, which is apogee, and then you got the minimum distance, which is perigee. So classical orbital elements, we call them COE. These are the most important elements for any object in space. እነዚህ ኳንቲቲዎች ናቸው አንድ ኦብጀክት የት እንዳለ እንዴት እየሄደ እንደሆነ ዲስክራይብ የሚያደርጉን በአጠቃላይ ኦርቢቱን ዲተርማይን ማድረግ የምትችሉት በእነዚህ ኳንቲቲዎች ነው። So የመጀመሪያው ሳይዝ ነው። So you got the size, you got the eccentricity, and እዚህ ጋር mu is a standard gravitation. Standard gravitation is constant for a planet. Standard gravitation equals to G times M, which is M is the mass of the Earth, and then G is the gravitational constant. So for any planet, there is always a standard gravitational measurement, and that gives you the size. Standard gravitational measurement divided by 2 times your apogee, or A, gives you the size of your orbit, and then you got eccentricity and your orbit. So how much time does it take to make a full orbit around a planet? So if you want to know that, you need to have your standard gravitation, which equals to G times m, which m is the mass of the planet, and then you got a. So a cubed, and then when you have a from your orbit, you can calculate the period of your satellite or spacecraft around that planetary orbit. So ሌላኛው lattice rectum ነው, or it's called parameter. When you have already have the eccentricity and then a, you can calculate your lattice rectum. And the other is radical distance as a function of orbital position. So when you have the lattice rectum, which is basically p is your orbital position, and then when you have p, using that you can calculate your radius r, your radical distance. So periapsis and apoapsis distances. So a is the major axis, the major from the center to the major axis, that's a, the value of a, and then you got rp, which is the radius of periapsis. You can find it with this formula, and then ra is given by a times 1 plus eccentricity. So comparing these two formulas, we can see that ra is always greater than rp, mathematically speaking. And also the angular momentum could be found with r is basically your position vector times your velocity at that specific point. So the magnitude could be calculated using the standard gravitation times the parameter and square root. That would give you the angular momentum too. So orbital elements. So orbital element በምናይበት ጊዜ 90 degree inclination ኦርቢቱ ከኢኳቶሪያል ፕሌን፣ ለምሳሌ መሬትን ለኤግዛምፕል ብንወስድ ከመሬት ኢኳቶሪያል ፕሌን ያላችሁ የሳተላይት ኦርቢት 90 ዲግሪ ከሰራ that we call it a polar orbit. Polar orbit ለምሳሌ ኢታሪስስ1 እንደ polar orbit አይነት እንትን ትራጀክተሪ ወይም ደግሞ ኦርቢት ላይ ነው ያለችው። ከ0 እስከ 180 ከሆነ ደግሞ we call that equatorial orbit, and then from 0 to 9 that's a prograde, and then from 90 degree to 180 degree that's a retrograde. So you can find the inclination with the two vectors hz and h. And then you have another classical orbital element, the right ascension. The right ascension is basically the angle between the longitude, ascending node የምንለው አለ። ascending node የሚባለው ከኢኳቶሪያል ፕሌኑ እና ኦርቢቱ ኢንተርሴክት የሚያደርጉበት አለ። ኢንተርሴክት የምታደርግባት ፖይንት ascending node ትባላለች። እቺ ascending node ከ reference direction ምን ያህል አንግል ነው የሚለውን ነገር እንፈልኩት በራይት ascension longitude ነው ማለት ነው። So you can have cos omega, and then nx divided by n would give you cos inverse of that would give you your right ascension angle. Argument of perigee ደግሞ it's also another orbital element. Argument of perigee ደግሞ ምንድነው describe የሚያደርግልን ኦርቢታችሁ አለ። ያ ኦርቢታችሁ ከኢኳቶሪያል ፕሌኑ እስከ ፔሪጂው ያለው አንግል ነው። ፔሪጂው ያለው የሚሰራውን አንግል ለማወቅ you're going to have argument of perihelion ወይም ደግሞ argument of perigee. It's also one of the classical orbital elements. So true anomaly also another orbital element which is used to describe your position with respect to the object you're orbiting. ለምሳሌ ፀሐይን ኦርቢት እናደርግ ቢሆን ከፀሐይ ያላችሁ የኦርቢታል ፖዚሽን አለ ፖዚሽን ቬክተራችሁ አለ። ያ ፖዚሽን ቬክተራችሁ ከኦርቢት ከምታረጉት ከሰን ለምሳሌ አንፃር የሚሰራው አንግል አለ። So that gives you it's changing at a certain point, ግን for a specific instant of time አንድ spacecraft or satellite or planet ያለው specific orientation or position በዚህ ማወቅ ትችላላችሁ ማለት ነው። So እንዴት ነው ኮምፒውት የምናደርገው? For example, when we have this given quantities, you have the position vector given in kilometers, and then you have the velocity vector given in kilometers per second. So using this information, we can calculate all of the classical orbital elements, including the A, the major axis, semi-major axis. You got the eccentricity calculated. You got the inclination, and then the right ascension, and then also the argument of perigee calculated, and then also the true anomaly with value of 0. So with value of 0 means that your satellite is in parallel with the object it's orbiting ማለት ነው። so ሁሉ ጊዜ ፊት ለፊት ያሉ ናቸው ማለት ነው። ፊት ለፊት ምንም አይነት አንግል አልሰራም ካለው ኦርቢታል ፊን አንፃር ማለት ነው። so ከዚህ mission we can say that probably a remote sensing satellite or a spy satellite because it's in low polar orbit. So remote sensing satellite basically ETRSS-1 ቅድም example ሰጥቻቸዋለሁ with orbital inclination of 90 degrees. So most utilized orbits lower Earth orbit ነው በዋነኝነት ሳተላይቶችን ማስቀመጥ እንፈልገው። mid Earth orbit አለ with 20,000 kilometers, and then geosynchronous orbit with 36,000 kilometers. So interplanetary trajectory እናወራ one of our last topics. So the main idea ምንድነው? interplanetary travel lower Earth orbit መጀመሪያ ሪች ማድረግ አለባችሁ። so lower Earth orbit ሪች ካደረጋችሁ በኋላ ወደ ሌላ orbit how do you go? So that we call it a HOHMANN transfer. HOHMANN transfer ተጠቅመን we can go from one orbit to the other. So orbits are very large. So ከእርዝ ስኬል አንፃር ለማስቀመጥ lower Earth orbit it's found around 300 kilometers. Most satellites are placed in that range from 300 to 700 kilometer range ላይ ነው የሚቀመጡ most satellites. So HOHMANN transfer እንዴት ነው achieve የምናደርገው? So we want to go from low Earth orbit to geo stationary orbit. So you have your initial low Earth orbit radius r1 and then your velocity v1. So using this formula you can have your delta v, and then using this formula you calculate your velocity. So you have your velocity at that specific radius, because the velocity does not depend on the mass of the object, but instead it depends on the mass of the object you're orbiting, for example the sun or the earth. In this case spacecraft ቢሆን m አለ, that m is it's part of earth's mass. ስለዚህ geostationary orbit ለመድረስ የሚያስፈልጋችሁ ስፒድ አለ። so እንዴት ነው accomplish የምናደርገው? so there's always a change in velocity ማለት ነው። so you are going to fire up your engines at this point, and then you can also fire up at this point, and then also you can do this at this point, and then you have a change in v1. So that change in v1 we call it an impulsive delta v. Delta v ያልነው ቀደም ዲስከስ እናደርግ is the change in velocity. ካላችሁ አንድ ኦርቢት ወደ ሌላ ኦርቢት ስትሄዱ there is always a change in velocity. How are you going to achieve that? The change in velocity is calculated using this formula. It includes your true radius for your velocity, your position vectors, and then it also includes the standard gravitation constant, and using that you can calculate the change in velocity. So once you achieve that change in velocity ከሰጣችሁት በኋላ ይሄንን change in velocity የት ወስዳችሁ ትከታላችሁ? ቅድም የተጠቀምነው rocket diffusion ላይ ያን rocket diffusion ተጠቅማችሁ ደግሞ how much propellant ነው burn ማድረግ ያለብኝ ከዚህኛው ከlower Earth orbit ወደ geo stationary orbit move ለማድረግ ማለት ነው። so ስለዚህ በርን በምታረጉበት ጊዜ መጀመሪያ ሪች የምታረጉት አፖጂን ነው። የመጀመሪያው ኦርቢታችሁ አለ። this is a transfer orbit. መጀመሪያ የምትፈልጉት ኦርቢት ይሄ አይደለም። የምትፈልጉት ኦርቢት በግሪን ያለው ኦርቢት ነው። ቀዩ ኦርቢት ደግሞ ትራንስፈር ኦርቢት ይባላል። it's just a transfer. you're not going to stay there. ግን አፖጂ ጋር መታችሁ ስፒዳችሁን ካላስተካከላችሁ you're going to stay በቀዩ ኦርቢት. even though lower Earth orbit ብትስተካከሉ you're going to stay in this elliptical orbit. so አፖጂያችሁ ጋር ከደረሳችሁ በኋላ ደግሞ you're going to do another burn ማለት ነው። so v2 ላይ ተደምጣሉ there is another change in v, so another delta 2. so ይሄንን delta 2 ታረጋላችሁ። ይሄንን delta 2 ድጋሚ ከተነጋገርነው ፎርሙላ you can calculate this ማለት ነው so the basic difference is በእነዚህ ሁለት ፎርሙላዎች mathematically በምታዩበት ጊዜ the interchangeability of R1 and R2 so ሁለት ጊዜ ነው ኢምፐልሲቭ በርን የምታደርጉት የመጀመሪያው ወደ ትራንስፈር ኦርቢቱ ለመግባት ሁለተኛ ደግሞ የትራንስፈር ኦርቢቱ ላይ አፖጂ ላይ ስትደርሱ ይሄን ትራንስፈር ኦርቢት ሰርኩላራይዝ ማድረግ ትፈልጋላችሁ ይሄን ትራንስፈር ኦርቢት ሰርኩላራይዝ ማድረግ ማለት ነው የዚህ ትራንስፈር ኦርቢት ሪጅን or the smallest distance ኢንክሪዝ ማድረግ ትፈልጋላችሁ ኢንክሪዝ በምታደርጉበት ጊዜ እየጨመረ ሰርኩላራይዝ ይሆንና ወደ ፈለጋችሁበት ወደ ጂኦስቴሽናሪ ኦርቢት circularize ያደርጋል ማለት ነው so the Hohmann transfer orbit discuss እናደርግ it's the minimum energy required mostly satellite እና spacecraftዎች የሚጠቀሙት ይሄንን trajectory ነው ማለት ነው እና it requires a lot of time basically again orbit transfer there's another method it basically have the same idea again it requires a higher change in velocity or delta v at the initial r ምክንያቱም even though ሁለተኛው ሬዲየስ ወይም ትራንስፈር ኦርቢት ላይ የሚያስፈልጋችሁ ቼንጅ ኢን ቬሎሲቲ ትንሽ ቢሆንም ኢኒሺያሊ ግን ካላችሁ ኢኒሺያል ኦርቢት ወደ ትራንስፈር ኦርቢት ራሱ ለመንቀሳቀስ ብዙ ቬሎሲቲ ቼንጅ ኢን ቬሎሲቲ ይጠይቃቸዋል ማለት ነው so no drag no maneuver near planet እነዚህ ነገሮች በአጠቃላይ ኮንሲደር አናደርግም ግን ቶሎ ትራጀክተሪ ለምሳሌ ቶሎ ወደ ጨረቃ መሄድ ከፈለጋችሁ change in delta ቢያችሁ በጣም ትልቅ ነው your change in velocity በጣም ትልቅ ነው ስለዚህ if you consider time in this equations even though time does not appear in these expressions if you consider time if you want to reach your destination at a faster rate you need to have a very high change in velocity so these are some of the summaries that we can do and then finally I can give you a lunar orbit insertion ምን ማለት ነው ቅድም እንደተነጋገርነው ከሎወር ኦርቢት ወደ ጨረቃ ለመሄድ ብትፈልጉ ምንድነው የመጀመሪያው የጨረቃ ቬሎሲቲ ማግኘት አለባችሁ so what is the velocity of the moon ሚት ማድረግ የምትፈልጉበት ፖዚሽን ላይ የጨረቃ ቬሎሲቲ ምን ያህል ነው የሚለው ማወቅ አለባችሁ ማለት ነው so ጨረቃ ስፔስክራፍቱን ከስፊር ኦፍ ኢንፍሉዌንስ ውስጥ ሲገባ ምክንያቱም ኦሬዲ ወደ ጨረቃ በቀረባችሁ ቁጥር እርዝ አይደለችም የእርዝ ግራቪቲ አይደለም አፌክት የሚያደርጋችሁ የሙን ግራቪቲ ይሆናል at a certain distance እና ያ ስፊር we call it sphere of influence so moon overtake የምታደርግበት ስፒድ የሙን ስፒድ around the earth minus your spacecraft speed at the opposite or the maximum distance from the earth ማለት ነው so ይሄ ቬሎሲቲ ምንድነው we call it hyperbolic excess velocity just because before you reach the moon spacecraft ያለው velocity hyperbolic velocity so the change in delta change requirement for lunar missions ለምሳሌ ከlower earth orbit ወደ lunar transfer orbit ለመሄድ your change in v1 is 3.1 km per second and then you can use this table to just understand ከlunar orbit ላይ ደርሳችሁ ከlunar orbit ወደ descent ለማድረግ land ለማድረግ የሚያስፈልጋችሁ change in delta v could be calculated with the formulas that we've discussed and then finally the planetary approach analysis it's the same as that and then you can use these formulas to calculate the hyperexcess velocity እንዳልኩት just before you encounter that planet spacecraft ያለው velocity ነው and velocity እንዴት ነው የምታገኙት using this change in velocity calculations ማለት ነው so this is all about our section in the advanced aerospace engineering so I think we've discussed most of the topics ranging from propulsion to orbital mechanics ስለሰጣችሁን ጊዜ እናመሰግናለን በቀጣይ ጊዜ እንገናኛለን thank you